Hi everyone. We are going to discuss on the topic solutions. So there is buffer solutions. Buffer is a support to maintain the pH of a solution. Which is the pH of the solution is very important, which cannot be altered any great extent by the addition of small quantities of either an acid or a base is called as a buffer solution. Here you can see that a small amount of a strong alkali is added, which is react with a H plus ion and is neutralized to water. If suppose any base is added, that is a react with the acetate ion and react to form the acetate ion. Some of the characteristics of a buffer solutions are as follows. It has a definite pH and the pH remains the same on standing for a long time and it does not change on dilution. The pH changes negligibly by the addition of small amount of acids or bases. You can easily visualize it by seeing these pictures. You see that pure water, that is the pH is equal to 7. In another pickup, we are adding water plus a buffer. Now, we are adding acid. So, in water, the water in which we are adding the acid, the pH turns to 3.2. And the beaker in which water plus buffer, the pH is about 6.8. And you can also see that after adding a base, suppose the pH is 11.5, it is a basic pH, and with the buffer, the pH is 7.2. You see that the pH is 6.8 and the pH is 7.2 are close to the neutral. Types of buffer solution: acidic buffer and basic buffer. So what is meant by acidic buffer? The mixture of weak acid and its salt. Example, very good example, acetic acid and sodium acetate and HC and sodium cyanide, boric acid and borax. These are all the good examples for acidic buffer. And then basic buffer, it is a mixture of weak base and its salt. Example, ammonium chloride, ammonium hydroxide, ammonium hydroxide, ammonium nitrate, glycine hydrochloride. Simple buffers. It is formed by the mixture of acid salt and normal salt of polybasic acid. Very good example is a phosphate buffer, that is Na2HPO4 and Na3PO4. So Henderson equation is used to calculate. Either we can use it to calculate or we can able to prepare the desired pH of the buffer solution. You see that how this Henderson equation is given for the acidic buffer. Here, that is acetic acid is a weak acid, so it is dissociated into acetate ion and hydrogen ion, which is irreversible. At a certain point of time, it will attain the equilibrium. Sodium acetate, which is a salt and it is a dissociated into acetate ion and sodium. So the Henderson equation is given by pH is equal to pKa plus log of salt by acid, where Ka is the dissociation constant of the acid. Similarly, in basic buffer, pOH is equal to pKb plus log of salt by base, where Kb is the dissociation constant. In general, according to Sorensen, pH plus pOH is equal to 14. That is, the minimum value is 0 and the max value is 14. Any solution whose pH will be lies between 0 to 14 only. Buffer capacity. So, yeah, whatever, even though it will maintain the pH which is very close to that, but to certain extent only it will be working. That is said to be the buffer capacity. So, how we can define it is buffer capacity is defined as the number of moles of acid or base added in 1 liter of solution as to change the pH by unity. That is that means if the pH or pH which will be increased, say for example 5 to 6 or 5 to 3 and likewise 10 to 11 or 10 to 9. So like that by changing unity how much amount of moles of acid or base is required to cause that the changes, that is called as the buffer capacity. So buffer capacity is equal to number of moles of the acid or bases added to 1 liter of the solution to change in pH. What are the applications of buffer in agriculture? Preservation of dairy products. You see, uh, in the food materials, we can have milk, we can take it. The milk is an emulsion which is very sensitive to pH. We can able to notice a drop of a drop or few drops of lemon or salt will be added to the milk, it will be denatured. So because this is because the protein which is sensitive to pH, if the pH changes, the protein structure and its functionality will be lost because that protein only stabilize the emulsion. So, in order to maintain a system, especially the dairy products, not only dairy products but all the food and beverages, pH it is very very important to maintain the quality as well as for shelf life and the important nutraceuticals. For pH is very very important. So, you know how to maintain the pH by adding the buffer. Industrial process like a paper industry, dye industry, ink and paint and drug industries. In all these industries, the pH it is very very important. If the pH is not to be maintained, we are not able to get the desired product, or else the quality of the product will be lost and the quantity will also be reduced. So, in analytical chemistry, pH is maintained during the titration to get the sharp endpoints or the sharp qualitative as well as quantitative analysis. In biological system, the pH is very very important. For example, in blood, the pH is to be maintained by 7.4. So, the nature itself provides a lot of buffer in our body to maintain the pH. In food industry, pharmaceutical industries, and chemical reactions, all are required the uh, maintenance of the pH for to get the quality and desired products. It is very very essential. So it is to maintain the pH by using the buffer solution. Then the Henderson equation we have to derive the use of the solubility product of the water. pH is equal to pKa of a log of salt by acid. That is nothing but conjugate base. So this is a derivation of this Henderson equation. The acid dissociation constant, the concentration of the product divided by the reactant, and we have to take the negative logs. It will be converted to minus log Ka is equal to minus log H plus A minus uh, minus log Ha. So minus log H plus is nothing but pH and minus log Ka is equal to pKa. When we are substituting, we are getting this one. The A minus is nothing but the concentration of the conjugate base, that is nothing but the salt, and this is the acid which will undergo the dissociation. Similarly, this is the Henderson equation derivation for the base, and the pH is equal to pKb plus log of salt by acid. So what there are certain limitations of this Henderson-Hasselbalch equation. It fails for strong acids and bases because they are using the equilibrium concept. So weak acids and weak base only undergo partial dissociation and will attain the equilibrium. Strong acid and strong base instantaneously dissolve and completely ionized. So this is not applicable for the calculating the pH. It is we can measure with the instruments only, and it is a self dissociation of water. So there is a chance of inaccurate for very dilute buffer solution. So very concentrated, it is okay. Very diluted buffer solution, this equation fails. Thank you.